measures against calculation errors. In the real world, no matter how precise a measuring device we use in measuring length, weight and other standards, there will still be errors. For example, if we measure a staff at 15.6 centimeters, we may find that the true length is 15.2595 etc. centimeters. Think about a test average calculated to be 57.87. In this case, unless there is a good reason for a very precise value, we can round it off to one decimal place and make it 57.9. There is no problem as long as we use it, knowing that there is an error in the value. Humans in the real world deal well with errors in this way. There are cases when data used in computers also contains errors. For example, 0.1 base 10 becomes an infinite fraction that cannot be represented accurately. Assuming the numbers after the radix point are represented using 24 bits, this becomes 0.099999 base 10, and an error occurs. However, when the error is very small, this number is used without problems for practical purposes. There are many kinds of errors. Let us look at the explanations of the typical ones. 1. Rounding error. Rounding off a number at a specific digit by either rounding it up or down is called rounding. Errors that occur from this process are called rounding errors. What would be the value of 57.87 if you rounded it up at the second place after the radix point? Two. Truncation error. In engineering calculations, when limit values and differential integral results are calculated, the repetition of processes makes it is possible to get even more precise results. However, after convergence has been confirmed at a certain value, the processing is stopped and the result is obtained. The error that occurs as a result of stopping this processing is called a truncation error. This differs from the true value calculated in mathematics. However, there will be no problem for practical purposes. Example: calculation of the circular constant, pi. Three. Loss of trailing digits. The loss of trailing digits is a phenomenon that occurs when the absolute value of a large number is added to or subtracted from the absolute value of a small number, and the small value of the absolute value is ignored. Example: think of a 24-bit Menticepart, 6-digit hexadecimal, and hexadecimal floating point number. The number with the big absolute value, the number of the small absolute value. When the exponent part is different, the operation is done after matching the small exponent to the big exponent, so the underlined part is ignored as if 0 had been subtracted. In order to avoid the loss of trailing digits, in the addition or subtraction of multiple numerical values, the numerical values are sorted so that the absolute values are lined up from the smallest, before adding or subtracting. By doing this, numerical values with very little difference in absolute values will be operated on, preventing the loss of trailing digits. Cancellation of significant digits. Cancellation of significant digits refers to the phenomenon that occurs in adding or subtracting two absolute binary values with the same sign that are almost equal, where the number of significant digits gets smaller. Example: think about the floating point number you used before. The underlined part is automatically generated as a result of normalization. The true digits are not all zeros. In other words, the figures below the first digit after the radix point are all unreliable. Because of this, it follows that the significant digits are reduced from 6 digits to 1 digit in hexadecimal. In order to prevent this cancellation of significant digits, the calculation is transformed so that subtraction of absolute values with the same sign that are almost equal does not occur.